Hello, everyone. My name is Steven, and welcome to week 2. This week, we will look at clips from 3 Brown, 1 Blue, Alexander Amini, and Nobel Prize lectures, starting with clip number 1.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number.
So for clip number 1, it explains that neural networks begin with no pre-existing knowledge. The weights and biases that determine how they process information start completely random. To learn, they use a cost function which acts as a measure of how wrong their predictions are. The goal is to make this cost function as low as possible by adjusting the network's internal parameters via an iterative process known as gradient descent. Moving on to clip 2 from 3 Brown and 1 Blue.
It's actually a nice non-spatial way to think about this. Each component of the negative gradient tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck.
So for clip number 2, the gradient vector of the cost function indicates the relative importance of each weight and bias. The gradient of the cost function is like a map, pointing out the direction the network should take to improve. It's a vector with multiple parts, each showing how much a specific weight or bias should be altered and in what direction. Crucially, the magnitude of each part tells you which changes will have the most impact on the network's learning. And moving on to clip 1 from Alexander Amini.
With times historically where the power of these systems was really called into question. And so that's why in the first part of this lecture, we really want to focus on some of the limitations that come with neural networks and deep learning. Because like any technology, right, it's important to be aware of what those limitations are so that we could best use these systems in practice. And so the first example that I always like to highlight is this notion of generalization. What do we mean when we talk about a neural network's capacity to generalize to new domains and new regimes? So to do that, I'm going to highlight this example from a past paper where they posed this really simple experiment, right? They took images from a large-scale image data set and said, okay, we have some ground truth labels.
So for clip number 3, neural networks are function approximators, and the universal approximation theorem indicates that a single layer network can approximate any continuous function. At their core, neural networks are function approximators. The universal approximation theorem suggests that even a simple single-layer network can learn any mapping between inputs and outputs. However, this theorem does not guarantee that the network will be able to generalize to unseen data, nor does it restrict the size of the network required. Moving on to clip 2 of Alexander Amini.
Original ground truth true labels to basically increasing amounts of randomness in the labels all the way to completely random. And as you may expect, right, as you increase the randomness in your labels, on that test set where you really care about the performance of that model, it drops off, the accuracy drops off. But what was really interesting was what they saw when now they looked at the accuracy on the training data. And this is what they saw, that no matter how much you randomize the labels, on the training set, you can eventually fit a neural network that will get very, very high accuracy, close to perfect accuracy. And what this shows and kind of illustrates is this concept that a powerful neural network, as powerful as it may seem, can perfectly fit to completely random training data.
So for clip number 4, I think neural networks can be tricked into fitting completely random data. This is an important finding because it means that even if the training accuracy is high, the model may have just memorized the data without truly understanding underlying patterns. Other failure modes include a lack of generalization to data that was not seen during training and algorithmic biases from issues in the training data. Moving on to clip 1 of the Nobel Prize lecture.
And its successors, AlphaZero, more general successors, mastered the game of Go and also all other two-player games through a process of what we call self-learning. So that's where these systems, instead of being programmed directly with solutions, they learn strategies and solutions for themselves. In this case, by playing many hundreds of thousands, in fact millions of games against itself, and incrementally learning from its mistakes and improving its strategies. And through this process of self-learning, we can build up a useful neural network model of Go. So AlphaGo and this 2016 result was a bit of a watershed moment, I think, in modern AI, as it was the first kind of big proof point that these sorts of systems, these kind of learning systems, were able to do something pretty impressive and thought to be intractable.
So for clip 5, we have DeepMind's journey to AlphaFold started with games, using them as a proving ground for AI due to clear objectives and abundant data generation. DeepMind's initial work focused on games. This allowed them to create complex problems where the objective was clear, like winning the game, and also generated lots of data by using systems that played against themselves. They were able to learn new strategies and develop the AI models required to tackle real-world problems. Lastly, we have the last clip, which is clip number 2 of the Nobel Prize lecture.
The diagram of the innovative architecture of AlphaFold 2. I'm going to leave John to cover some of the technical details of this in his talk, but the high-level thing, that takeaway is that actually there was no silver bullet to solving this problem. AlphaFold 2 actually had to incorporate over a dozen different innovations into quite a complex, what we call a hybrid system. And one of the key things of that was to build in evolutionary and physical constraints into the architecture, along with the learning components of the system, and sort of combining those two elements together. And it was key to that the fact of this working is that the AlphaFold team was a multidisciplinary team composed of expert biologists and chemists, as well as machine learning and engineering. And it was a full end-to-end system that started with the amino acid sequence and directly output the 3D structure prediction. And it used this sort of recycling stage that allowed it to iteratively refine.
For clip number 6, I was able to only get 1 minute of the video because the whole entire highlight was way too long, so I'm just going to explain it in this slide. So this highlights a key breakthrough in AI, the ability of systems to learn and improve without explicit programming. AlphaGo's success was not due to brute force calculation, but rather its capacity to learn strategies through self-play. The system's neural network model enabled it to navigate the complex game of Go by focusing on the most promising moves, efficiently and effectively using a model of the game. This self-learning approach demonstrated a significant advancement in AI, and the techniques were later applied to other real-world problems, including the protein folding problem of AlphaFold. The neural network allows the system to efficiently consider only a small fraction of all possible moves. This ability to learn from experience and optimize strategies paved the way for the future advancement in the field of AI. By focusing on the self-learning approach and efficient use of the neural network model, this slide helps illustrate that the core principle that made AlphaGo so revolutionary and connects the principles to later work in sciences. Well, that wraps up my week 2 video. I hope you guys enjoyed it, and I'll see you guys next week.